Welcome to our channel, Sairam Educational Channel. In this particular lesson, we will see the haloalkanes, that is substitution nucleophilic unimolecular reactions. Substitution nucleophilic unimolecular reactions. We have seen in the previous videos that substitution nucleophilic bimolecular reactions, how it happens. That is, alkyl halides undergo substitution reactions with the nucleophiles, and it happens in a single step in the bimolecular reaction where the nucleophile attacks the central carbon atom to which the halide atom is attached through the rear side, and halide goes from the front side. Both happens at the same time, and there are two molecules involved in that particular reaction. One is alkyl halide and the nucleophile. Both are important, so that's why the reaction mechanism we called it as substitution nucleophilic bimolecular. But now if you can see substitution nucleophilic unimolecular, it was a little different than that one. For example, if I take a tertiary alkyl halide like this, it is the carbon having 3 methyl groups and bromide ion. And it was attacked with a nucleophile OH minus ion, then we will get tertiary alcohol. That is 3 carbons, 3 methyl groups over this carbon and 1 OH group. That is, the name was given 2-methyl propane 2-ol. So these SN1 reactions generally carried out in polar solvents, protic solvents like water, alcohol, acetic acid, similar to that. And it happens, if you can see the mechanism, it occurs in 2 steps. The step 1 is the important step here because that is the slowest step. So it should be the rate determining step. So this alkyl halide first need to convert into carbocation and the leaving group as bromide ion. This carbon and bromide bond should break. So the cleavage of carbon bromine or carbon halide bond is important for the substitution nucleophilic unimolecular reaction. Whichever compounds able to cleave the bond between C and Br, they will easily participate into substitution nucleophilic unimolecular reactions. In this step, you can see this is a reversible reaction. It can happen both directions. So the CBr bond, if it is very strong enough, the compound would prefer to be in this form rather ionizes. But if the carbon Br bond breaks, the Br takes the electrons between the carbon Br bond, so carbon becomes plus. This is the carbon becomes plus, and it is a carbocation. Carbon is having positive charge, so it is called a carbocation. Now this carbocation further reacts with the nucleophile. In order to happen this step, you remember these carbocation, what are formed in the previous reaction, should be stable enough to participate in the next step. So the carbocations which are more stable, which formed in the first step, can only further participate with the nucleophilic attack, and they will undergo the nucleophilic substitution. Now OH can come and attack over the carbon, then you will get the CH3 thrice COH. This is that particular compound. These are the 2 steps in which the reaction happens. I hope you understood. Can you see once again we can explain this. I have a tertiary alkyl halide. In the first step, the alkyl halide ionizes. We can say that's what we did these reactions in polar solvents, protic solvents, which makes them these carbocations to form easily. Once this forms, only the reaction proceeds further. If the carbocation didn't form in the first case, then there is no further reaction as per SN1. So that's why the CBr bond breaks and Br becomes Br minus and carbon becomes positive charge. This carbocation gets stabilized. And you know tertiary carbocations are more stable than secondary than primary because of the no bond effect, resonance effect. So this is the way we can say this carbocation is more stable, and this carbocation now attacked with the nucleophile incoming nucleophile and forms the nucleophile substituted compound. And if you can see this, the step 1, as I told, it is the slowest and reversible step, and it involves the breaking of the CBr bond. And the rate of reaction depends only on the first step. What is the first step? That is the breaking of the bond between carbon bromide. That is the involvement of alkyl halide. So the concentration of alkyl halide, the rate of the reaction depends. So the rate of reaction depends upon the concentration of alkyl halide, but not on the concentration of hydroxide ion, which is a nucleophile. So the alkyl halide, which will break due to solvation of the halide ion with the proton of the protic solvent. That's why these reactions generally does in protic solvents. If the stability of the carbocation is higher, its formation to the carbocation from the alkyl halide is easier, faster. So the first reaction will be faster, then the reaction rate will be higher, because that is the rate determining step. In case of alkyl halides, I told tertiary alkyl halides gives stable carbocations, so they prefer to form SN1 reaction. So that's why tertiary alkyl halides, for SN1 reaction, the rate of reactivity is higher for tertiary than secondary, than primary, than methyl halide. So if you can take these alkyl halides from methyl halide to primary halide, where I can have even ethyl halide or one more, ethyl halide, etc. And then you have a secondary halide, then primary halide. If you can see, the SN1 reaction rate increases from primary to the tertiary, and SN2 reaction rate decreases from tertiary to the primary. You know SN2 why it is decreasing? Because tertiary halides will be bulkier. The nucleophile has to attack the central carbon through the rear side. So there should not be any steric effects. That is, space should be available around the carbon size the nucleophile can easily attack. That is possible only in the primary halides. But in the tertiary halides it is difficult. That's why SN2 reaction prefer to happen in primary alkyl halides rather tertiary. But SN1 reactions, the concept is different, where two-step mechanism is happening. In the first step, the formation of the carbocation is very, very important. The carbocation which are formed should be more stable. Such carbocations only can form from the alkyl halides. So when you take a tertiary alkyl halide, once the carbon halide bond breaks, the formed tertiary carbocation is more stable. So tertiary halides undergo SN1 reaction. This is the simplest way one can able to understand. Generally, in a similar reason, allylic and benzylic. Allylic, this is the sp3 hybridized carbon to a double bonded carbon is allylic. In this allylic, CH2 double bond CH2 plus. It is a allylic carbocation. But if it is a halide, this CH2X will come over here. So CH2 double bond CH2X, that is allylic halide. And this is the benzene, and this is benzyl. And here if I have X, this is benzylic halide. Both allylic and benzylic halide, remember such questions will be asked in examinations. Both allylic and benzylic halides show high reactivity towards SN1 reactions, because the formed carbocation, once the carbon halide bond breaks, you will get a carbocation like this in allylic case, and in benzylic case, if the X breaks here, CX, then you will get a carbocation like this. These carbocations are more stable. Since they are more stable, they easily forms. They get stability by the effect called resonance effect. A resonance effect. The movement of the pi electrons. You see, these are the double bonded. They will be delocalized with this positive charge. Since carbon is having, this bond can move and positive charge comes over here. You see, these are two resonance forms. They are highly stable. They are similar resonance forms. You can see CH2 double bond CH2 plus and CH2 double bond CH2 plus. They are equal resonance forms. If they have equal canonical forms more, they are also called canonical forms. They are more stable. So this carbocation is stabilized by a resonance effect. And if you can see this benzoylic, this also gets stabilized by the resonance. What happened? Positive charges over this carbon, so it tried to take these two pi bonded electrons here. Then I get a double bond over here, then here positive charge. That's what's seen here. Once there is a positive charge near to a carbon, it tries to take the pi bonded electrons which are loosely held towards that side. Then we will get here positive charge because this carbon electron is moved towards this. So we will get here positive charge. That's what here. Then the next movement happens here, then you will get positive charge here. Then it comes over here, then you will get positive charge. That is this one. So I can write 4 canonical forms, 4 resonance forms. So due to resonance, since the carbocation formed carbocation in the first step, that is the slowest step, is more stable, the products are more preferred to form. That means carbocation forms. Once the first step stable and the carbocations forms, it further easily reacts with the halides. That's why allylic and benzoylic halides show high reactivity towards SN1 reaction. So we see now what type of alkyl halide participates more in SN1 and SN2. Now you see in this SN1 reaction, the reactivity for a given alkyl group, the reactivity of the halide follows this order. You see the halides, you have alkyl iodides, alkyl bromides, alkyl chlorides, alkyl fluorides. The R becomes plus, that is carbocation formation happens once this bond breaks. So breaking the bond depends upon the stability of the carbocation. First we have seen here, if CX bond easily breaks when the carbocation is more stable. At the same time it also depends upon the nature of the bond. Nature or bond length. How the bond length will vary? Here you see I is a bigger atom when compared to F. The bond length is higher. Atoms are far away each other, so the bond can break easily. With respect to the halide, if we can consider Ri bond is weaker than RBr bond, then RCl bond, then RF bond. Since Ri bond is weaker, it forms easily carbocation. That means iodide ion is a better leaving group than bromide ion, than chloride ion, than fluoride ion. Why we say a leaving group? Because this iodide is only the one which is replaced with an incoming nucleophile. So this I minus is the leaving group. It leaves from the compound. So they can also ask which is the better leaving group, whether iodide, bromide, or chloride or fluoride. Remember, the bond length is higher since the atom size is bigger. Iodide is the better leaving group than bromide, than chloride, than fluoride. So this is the way it was given, and here also one example was given. In the following pairs of halogen compounds, which would undergo SN2 reaction faster? Remember, SN2 primary alkyl halides more than secondary than tertiary. So you can see this compound, particular compound, this is a primary alkyl because carbon linked with the halogen is having only one alkyl substituent or one. This is a cycloalkane, so one alkyl substituent. So it is a primary alkyl halide. So it prefers to undergo SN2 reaction faster. That is obvious. And if you can consider the second one, this chloride containing carbon is having two more alkyl substituent. They are considered as fragments. They are also called as alkyl substituent. That means it is a secondary. So in the first case, this is the one which undergoes SN2 reaction faster when compared to this. But if you can consider the second one, as I told, Ci bond is here CCl bond. Which is the better leaving group? Iodine. So as iodine is a better leaving group, because of its large size, bond length is higher, it will be released at a faster rate. So that's why the iodides undergoes SN2 or substitution nucleophilic reactions with high reactivity. Okay, both are primary alkyl halides, so that's why they are undergoing SN2 reaction. Okay, so this is, and another one also they have given, predict the order of reactivity of the following compounds in SN1 and SN2 reactions. So now you need to arrange them. For SN1 reaction, what is the order? SN2, what is the four isomeric bromobutanes and this particular compounds. You see the bromobutanes, four bromobutanes were given here. You see carbon is attached to first bromine. Here also attached to first bromine, but there is a branching at the third bromine, third carbon. So like this was attached to the second position. The next is three branches. Carbon is having three methyl groups. Here carbon is having one side methyl, one side ethyl group. Here carbon is having this isopropyl group. So like this it is an armor group. So these are the four bromobutanes. All are bromobutanes. You have carbons 4 and bromine. So these are all bromobutanes. For SN1 reaction, you know that is the tertiary carbocation. That is tertiary alkyl halide is the more reactive. This is the tertiary because carbon is having three methyl groups. That is three sides you have methyl groups. So this is the tertiary alkyl halide which undergoes SN1 reaction faster. Then this one, if you can take bromide is here, one side ethyl group, one side methyl group. So it is a secondary. Next reactivity is this. And if you come to this is a primary. So reactivity is this. But the primary substitute is CH3 twice. It is a branched chain. That's why when compared to this straight chain, this reactivity will be a little higher. Then you comes to the normal one. In the case of SN1, that is the carbocation stability we have to consider. Once it forms, how the carbocation is more stable. Based on that, we are telling here. So normal primary alkyl halide will be less reactive. And if you can see, this primary alkyl halide is the one more reactive for SN2 towards. So you can just reverse the order for SN2 reactions. So this is the way it happens. And another compounds which was given is this particular compounds, and we have seen in the previous page. So there also we need to identify the SN1 and SN2. SN1 prefers to happen in more tertiary, but this is a primary because alkyl halide becomes a substituted alkyl halide, that is benzyl. We seen already benzyl bromide. It undergoes SN2 reaction rather SN1 because of the primary nature. So it prefers to be SN1. So SN1 reactivity is higher, SN2 reactivity is higher, SN1 reactivity is less. So based on that you can easily identify which will form faster and slower. Okay, thank you. We will see in the next video some more part of this particular lesson. Please do subscribe the Sairam Educational channel for further updates. If you have any clarifications, please let us know.